All right, last strategies for today, and this is where we're going to make trigonometric substitutions. So we are going to be going from an integral that doesn't have trigonometry into it and putting trig there. And that might seem counterintuitive, but it's going to create some very nice situations sometimes. If you see in a problem, square root of something squared minus x squared, we're going to use the substitution x equals a times sine theta. And why would we do that, you might ask? Well, it goes back to right triangle trig. If this is theta, sine of theta is x over a. So sine is opposite over hypotenuse. And using the Pythagorean theorem, this third side is a squared minus x squared. And a similar kind of thing can be used for these other two substitutions that we're going to do. But if we see square root of x squared minus a squared, we're going to make the substitution x equals a secant theta. And finally, if we see square root x squared plus a squared, or a squared plus x squared, doesn't really matter, we're going to use x equals a times tangent of theta. And tangent, secant, sine, these are all things that are related to the Pythagorean identity also, which we will be using in these examples. First example, the integral square root 25 minus x squared dx. All right, so going back to the previous screen, what do we use when we see something squared minus x squared? We're going to use x equals a sine theta, so 5 sine theta. And dx would be 5 cosine theta d theta. Okay, so what does this radical become? It becomes, and I like to do this without the integral sitting there. We have 25 minus 25 sine squared theta, and we can factor 25 out. And the square root of 25 is 5, and 1 minus sine squared is cosine squared, and the square root of cosine squared is just plain cosine. So what does our integral become? Well, that whole radical piece, we just showed that that can be reduced down to 5 cosine theta times dx. dx was 5 cosine theta also. And so we have the integral of 25 cosine squared theta d theta. And if we've been paying attention in the previous videos, we know how to deal with cosine squared theta when we're taking the antiderivative of it. We're going to use that double angle identity. We have 1 plus cosine 2 theta over 2. And these are things that we can take the antiderivative of. We're going to think of this as being 1/2 plus cosine 2 theta over 2. So we have 25 times theta over 2 plus 1/4 sine 2 theta plus c. And we're going to distribute. So 25 theta over 2 plus 25 over 2. But we don't want to leave sine 2 theta there. What we actually want to do is just have it in terms of boring, uninteresting theta. But sine 2 theta is 2 sine theta, cosine theta, and plus c. So we have 25 theta over 2 plus 50 over 2 sine theta, cosine theta, plus c, and we're going, yes, we're done, but we're not. Again, just like in the other substitutions, we have to bring this back in terms of x. And remember we made the substitution x equals 5 sine theta. That means that sine theta is equal to x over 5. Well, that's cool. I can replace sine theta with that. And we also know that theta is the arcsine of x over 5. So I can replace sine theta, I can replace theta right now, but I still need cosine theta. And we could use a Pythagorean identity, or we can go think about a right triangle with this. Here's theta. We have sine being x over 5. That means this last side is square root of 25 minus x squared. You know, that thing that we substituted into. So cosine theta is root 25 minus x squared over 5. And now we have all the missing pieces. So we have 25 over 2 times the arcsine of x over 5 plus 25 over 2, and I made an oops back here. This should have been over 4, 25 over 4, and 50 over 4. So that times sine theta, x over 2, times square root 25 minus x squared over 5 plus c. And we could do a little bit of cleaning, a little bit of simplifying with that last term. Becomes x over 2 square root 25 minus x squared plus c. And there we go. We have just finished our first trigonometric substitution into an integral. Okay, so if you recall, we've looked at the antiderivative of secant theta, d theta. It was equal to the natural log of the absolute value secant theta plus tangent theta plus c. Little ditty that we're going to need in this example, so please don't forget about it. So we have the antiderivative of 1 over square root 3x squared minus 48. Ooh. Now, the thing with this is that's not written in any one of those three forms. It's almost x squared minus a squared, but it has that coefficient of 3. So before we can do anything, we actually need to factor that out. And so what we have now is 1 over square root 3 times the integral 1 over square root x squared minus 16 dx. And when we have x squared minus a squared, what do we do, ladies and gentlemen? Look back at your substitutions. We're going to let x equal 4 secant theta, which means that secant theta is equal to x over 4, and cosine theta is equal to 4 over x. I'm just writing down some stuff that I know from that. We also know that dx is equal to 4 secant theta tangent theta d theta. Derivative of secant is secant tangent. So let's build our triangle real quick. This will be helpful in all of these problems. So cosine is 4 over x. That means this last side is x squared minus 16. And we'll use this when we make our substitutions. later on down the road. But now, what happens with this denominator? Square root x squared minus 16. Well, we substitute in our 4 secant theta. So we have 16 secant squared theta minus 16. Factor out the 16. So we have 4 square root of tangent squared by the Pythagorean identity. So 4 tangent theta. Okay, so our integral becomes 1 over square root 3 times the integral 1 over 4 tangent theta times dx. So times 4 secant theta tangent theta d theta. And, oh golly, the tangents cancel. We have 1 over square root 3 integral of secant theta d theta. And I said we'd need the integral of secant theta, and here's where we need it. 1 over square root 3 times the natural log, absolute value, secant theta plus tangent theta plus c. And now we need to make substitutions for secant and for tangent. So I'm coming back over to my triangle. Tangent theta would be equal to the square root x squared minus 16 opposite over adjacent, which is 4. So secant theta was x over 4. And since they're both over 4, we'll just do the whole thing there. Plus square root x squared minus 16 plus c. And, okay, so what happens now? Well, using properties of logs, we can break this apart, numerator and denominator, into 2 different logs. Using subtraction. And this whole thing right here is just some constant. So our finished answer, our finished antiderivative of that original thing written in black up there, is 1 over square root 3 times the natural log of absolute value, x plus square root x squared minus 16 plus a constant, whatever you want to call it. And there we go. We have finished this example. 1 over square root x squared plus 2, the integral of that with respect to x. So, x squared plus a squared, we use the substitution x equals a tangent theta. So a here would be square root 2. So tangent theta is x over square root 2. Let's see, we need dx. What's the derivative of tangent? Well, it's secant squared. So our triangle that we could set up, which will be used later on, I like to get this out of the way right now. Tangent is opposite over adjacent, making the hypotenuse x squared plus 2. Cool. Well, what does our integral become? The square root x squared plus 2 becomes 2 tangent squared theta plus 2. Factor out the 2. Square root of 2 times the square root of secant squared theta. So square root of 2 secant theta. All right, so what does our integral become? We have 1 over square root 2 times 1 over secant theta times dx, which is square root 2 secant squared theta. And remember to multiply by that dx. That is important. You can't forget about it. So this now becomes, well, the 1 over square root 2 cancels, so it's just integral secant theta d theta. Isn't that lovely? We just talked about what that is. That's equal to the natural log of secant theta plus tangent theta. And secant theta from the triangle, that would be 1 over cosine theta. Cosine theta is root 2 over root x squared plus 2. So secant is going to be square root of x squared plus 2 over square root 2 plus tangent theta, which is x over square root 2. And since they're both over square root 2, let's just combine them into one fraction. And again, we can use properties of logs. Natural log x squared plus 2 under the radical plus x minus natural log square root 2 plus c, and this whole part again is a constant. So our finished antiderivative is natural log of absolute value root x squared plus 2 plus x plus some constant, I'll call it d, and there we go. These methods that we've looked at in the last 3 videos serve to recreate the function in terms that we can actually find antiderivatives for. It's a really slick process. It's kind of neat if you think about how we can turn this thing that we can't do anything with and suddenly be able to find the antiderivative very easily. It's kind of cool. So get some practice. These questions do get long. There's a lot of algebraic manipulation that has to happen. So please be very organized and meticulous in what you are writing for these problems.